Hello, welcome to today's video. Today we're looking at transformations in the X direction specifically. We're going to be looking at the three main transformations types of translations, stretches, reflections. I'm sure there'll be timestamps in the video description so you can skip to any of them if there's a particular one you want to look at. So heading straight into it. What is the general idea of X direction transformations? Well, the best way to describe that is to point out the contrast with what happens with Y direction transformations. Y direction transformations are all about looking at the function as a whole, the f of x, and applying an action to that f of x, almost as if that f of x is in brackets. So whether that's multiplying the brackets out by a number, adding a number on the end, and that's just how adding works with brackets, you're still doing something to the function almost as a sort of a whole. Therefore, it's often fairly easy to spot Y direction transformations because most of the function will have changed. If it's a stretch or if it's a translation, then you're just looking for what's happened to the constant. X direction transformations are different. Instead of applying it to the function as a whole, it's all about just changing what's happening to the x. And the way you're going to do that is by replacing the x with something else via a substitution. So all you're going to notice in the notation is something inside of the f of x. This bit here is what's going to change. And then also in the actual function, we're just going to be replacing every term or every place where an x appears in the equation with something else involving an x. Therefore, that means straight away with an x direction transformation, if you have a constant term, that will never be affected by an x direction transformation. And so that's often a key clue if there is a constant term for whether something has been a y direction transformation or an x direction transformation. Okay, so the two main things therefore to remember are that it always is applied by a substitution. And just confirm, yes, I'm talking about the x direction transformations now. But then the other thing to point out is how this looks on terms of the actual equation. As far as the wording goes, what the wording says is still fairly logical in terms of the wording tells you what's directly happening both graphically and also to the coordinates. In other words, we'll look at it more later, but a stretch scale factor 2 parallel to the x-axis is still doubling or multiplying all the x coordinates by 2. So that part is still logical. However, what happens to the actual equation is a bit less obvious. What happens to the equation is the action that we're describing the words is the inverse of what happens to the actual function, or at least the substitution we're doing. So therefore, I'd say x direction transformations always apply the inverse action to the equation. As part of the substitution. So that's probably not the most eloquent way to word it. I think the best way, ultimately, is just to show you examples, and you'll quickly see what I mean, hopefully. So first one to look at would be translations. And once again, best way of wording it would be just a translation. Just use the word translation. Don't use the word move. And then once again, just use a vector. A lot easier, a column vector, a lot easier than having to write it out in words. Now, as far as the notation goes, what we're going to be doing is f of x is now going to be replaced with f of, the x is not going to be there anymore because that's what we're doing. We're going to be doing it by substitution. X is going to be replaced with x minus a. Now, the things to point out there, just like before, translation is related to adding and taking away. But just like I said just earlier, it always does the opposite of what you think it's going to do. So if we're doing a translation positive a0, in other words, that would be moving it to the right, even though that's not the official wording, then what we see happening to the function is kind of the opposite of that. What's the opposite of adding a? Well, it's subtracting a. So that's what ends up happening with the substitution. So basically, every x in the equation is going to be replaced. You're going to replace it with x minus a. So in the equation. So an example, well, we could look at a quadratic, and then we could look at something a bit more complicated using the same classic quadratic I've used a couple of times in the previous video. Y equals x squared minus 2x plus 5. I actually can't remember if that was the right quadratic now, but never mind. And we're doing a translation, let's say minus 4, 0. Then what we're going to do is it means we're going to replace the x, every x in the equation, with x minus our number we're translating it by. But because we're translating it minus 4, x minus minus 4 is, of course, x plus 4. So therefore, every x is being replaced with x plus 4. And I mean, if you're writing using the posh function notation, f of x is going to change to f of x plus 4, I said. And therefore, the equation is now going to be, well, it was x squared, but now therefore it's going to be x plus 4, x plus 4 all squared. Then take away 2 lots of, it was x before, but now it's going to be x plus 4, and then plus 5. Now, if you wanted to, you could multiply out the brackets and you'd eventually, simplify and get what the quadratic looks like. However, if you do that, it does become, it's worth mentioning if it has been written like that, a lot more difficult to spot the transformation that's occurred. But that's, by the way, why completing the square exists for quadratics in particular, as it's an easy way to then rewrite it in terms of these brackets with the squareds and stuff to then see what's happened. Doing another example quickly, if we have y equals 3 to the x minus 3, and we want to do a translation of, let's say, 2, 0, then what's going to happen is we're going to go from the original function, which was f of x, and we're going to go to, well, the amount we're translating by is 2. X direction does the opposite of what we think it's going to do, so instead of positive 2, it's minus 2. So it's f of x minus 2. So that means every x we see in the equation, in this case it's only one of them, that x though is going to be replaced with x minus 2. So therefore after the transformation it's going to come y equals 3 to the power of, it was x, but therefore now it's x minus 2. Make good use of brackets, by the way. I didn't mention that before, but you saw that I could use brackets a lot. Make good use of brackets to make sure that whatever action was happening to x before is now happening to your replacement for that x. And therefore, it's x minus 2 minus 3. Which, of course, yes, in this case, it would make sense to a certain extent to simplify because that's such an easy one. You could, of course, simplify that to y equals 3 to the power of x minus 5. Okay. So that's how you can, a couple of examples of applying an x direction transformation. Going back to what happens to the coordinates though, well, as I said before, the coordinates actually do more what's happening with the wording rather than what's happening to the actual equation. So if we have the coordinates for 9 and we decide to do a translation, let's do something crazy like 19, 0. Ooh, 19. It's not crazy at all, but hey. A translation 19, 0, that logically means we're moving it 19 units to the right. In other words, we're literally just going to add on 19 onto the x coordinates. Directly what the wording says is directly what's going to happen to the coordinates. So therefore, the new coordinates will be 19 plus 4, which is 23. And then the y coordinate doesn't get affected at all. X direction transformations don't affect y coordinates. Okay, now moving on to stretches. This time, similar to before, the wording has to be careful. We write it as a stretch scale factor, and we could use a different letter. Let's use this letter M, scale factor M, parallel to the x-axis is one option. Or a stretch scale factor, again, we could use M, in the x direction. So those are the two possible wordings. Again, avoid saying in the x-axis when we're talking about stretches. Okay, so how do these get applied? Well, again, you start off with f of x is the original function, and if that's the original function, then the transformed version of that function would be f of. Again, we're going to be replacing the x with something else via substitution. Stretches are to do with multiplying, but therefore we're going to be doing the opposite of what we expect to see in the wording. So if you think, what's the opposite of multiplying by m, which is what we'd logically think it would be dividing by m, but we still want to write it as a multiply, so writing a division as a multiply is the same as doing timesing by 1 over that amount. So multiplying by 1 over m is the same as dividing by m. So therefore, we're going to replace our x with 1 over m lots of x. Where m, of course, as I said above, is your scale factor. So quick example, stretch scale factor, let's say 9, parallel to the x-axis. And again, applying it to a quadratic, y equals x squared minus 2x plus 5. I can't even remember what quadratics I was doing anymore. Every x in this case, therefore, is going to be replaced with 1/9 x, using the rule I said above. So therefore, everywhere I see an x, put brackets around where the x originally was, to therefore make sure that everything that was happening to the original thing is now happening to its replacement as well. So therefore, it's 1/9 x, all being squared. Take away 2 lots of, it was x before, but now it'll be 1/9 lots of x. And then plus 5 doesn't get affected at all because it's just a constant, no x, so therefore we've got nothing to replace. Once again, though, if we're looking at the coordinates, if we got the coordinates 4, 9, and we want to do a stretch scale factor, let's say 1/10, or no, let's say keep it simple, 10 in the x direction, then what does that do? Well, for the coordinates, it does exactly what the wording says, a stretch scale factor 10, in other words, multiplying by 10. So the x coordinates just get multiplied by 10. It's only the function that sort of acts in the weird way where it does sort of the opposite of what we expect it to. Okay, so that's stretch. Last one we're going to look at is a reflection, and the wording is again key because for reflection in the x direction, because that's what we're grouping it with, this would be a reflection in the y-axis. Now, if you want the reason why we're allowed to use the word in and y-axis, have a look at the video I did for y-direction transformations. But basically, the moral of the story is it's because the y-axis is our mirror line in this case. That's why, despite being grouped as an x-direction transformation, the y-axis is being used as the reflection line. Movement is still happening left and right. Okay, so how are they done? Well, as I said before in the y-direction video, that reflections are effectively stretches with a scale factor of -1, and so it's no different here. Therefore, we could replace f of x with, or the x in f of x with, well, if using the logic above, it should be 1 over -1 lots of x, because it was a stretch scale factor m was 1 over m lots of x. See, the thing is, though, 1 over -1 lots of x is just the same as f of minus x, just because -1 divided by -1 happens to be -1. So it's worth pointing out it is consistent with the logic I said above. It's just that as it happens, 1 over -1 just ends up getting us -1 in the end anyway. So going through an example of that, if we have, again, quadratic, unimaginative, I know, but let's say y equals x squared minus 2x plus 5, and we want to do a reflection in the y-axis, then all we're going to do is we're going to replacing x in the original function with minus x everywhere in the equation where an x appears. So therefore that means the equation is going to become, well, it was x squared, so technically it's minus x all squared. As it happens, if you were to then multiply out the brackets, interestingly, minus x all squared is just x squared in the end. So ironically, not much effect there. But if we're wanting to show the action taking place, this is what we'd write still. And therefore, minus 2, lots of minus x now, and then the plus 5. So there you go. That's all there is to it. As far as applying it to coordinates, you probably got the idea, but it's the same logic. It does what it says on the tin in terms of the wording versus what you see happening to the coordinates. So if we have the coordinates 4, 9, and we do a reflection in the x-axis, not in the x-axis, in the y-axis. Oh, I knew I'd get it wrong eventually. A reflection in the y-axis, that just means we're going to literally multiply the x coordinate by minus 1. So it becomes minus 4, 9. There you go. So that's all the x direction transformations. Hopefully that was useful for you. Something I didn't really mention in terms of spotting them. The way you spot them is you're all just looking for, I mean, the key thing is if they're kind, they've written things in brackets like this. That makes it easier to spot that a substitution has happened. The fact that x has been replaced, and then you've got a new thing in place of it. So that's often the big clue. That won't always be the case though, because sometimes there won't need to be brackets there. So you've just got to be aware of the fact that it's not happening to the equation as a whole. Like you haven't multiplied the entire equation consistently by the same number, or you haven't added a number on the end. It's all about, for instance, I mean, another example would be, well, we have lots of different things, but if we have 1 over x plus 3, and we did a stretch scale factor 1/5, then what we would do is it would go to y equals 1 over 5 x plus 3. And so we didn't put the brackets there because we didn't really need to. But the key thing is it's just the x that's changed. Everything else in the equation is as it was before. Okay, thank you and goodbye. I'm sure I'll see you in a future video.